Hi, everybody. So my name is Nicholas Armada. I'm going to be talking about transient absorption spectroscopy today. Thought it was a pretty interesting technique. Kind of touched on some of the concepts that we covered in class over the semester, and it's also somewhat related to my research field. So I'm going to just get right into it. So I'm just start with just a presentation outline. So first, I'm just going to start with a brief introduction to the technique and talk about the photophysics of molecular electronic states. I'm going to kind of revisit the Jablonski diagram that we discussed in class earlier on in the semester. I'm going to talk about a brief overview of the technique. And then I'm going to go into the instrumental theory and then the physical basis behind how this technique is carried out. And then I'm going to go into the spectral features of transient absorption spectra, as well as the data analysis. And then I'm going to talk about some applications in organic photocatalysis and organic reaction methodology. And then I'm going to touch on one noteworthy example from the literature. It's a paper, it's a mechanistic paper from the Doyle group at Princeton University. Then I'm going to wrap up with just a brief summary and some concluding statements. So here I have the Jablonski diagram, similar to what we saw in class earlier on in the semester, and just going to briefly go over it just as a quick refresher. So so here we have our singlet ground state, which is where most molecules exist. And upon absorption of a photon, the molecule can be excited to an excited singlet state where, so we have these quantized energy levels here. But from the singlet excited state, you can either decay back down to the ground state through a process called internal conversion, which is a non-radiative process. So typically this is going to be through some sort of thermal mechanism. And then you could also decay from the singlet excited state back to the singlet ground state radiatively through a process called fluorescence, where a photon is emitted. Alternatively, you could also spin flip to a triplet excited state through a process called intersystem crossing. So this is where we're kind of losing the spin coupling of our electrons. And from the triplet excited state, you can either decay down back to the singlet ground state, again through internal conversion, or through a spin forbidden process. You could also spin flip back down to the singlet ground state radiatively through a process called phosphorescence. And then also you could also spin flip back to the singlet excited state through a process called reverse intersystem crossing. And then you could either decay back down to the singlet ground state through internal conversion again, or you can relax back down to the ground state radiatively through fluorescence again. And in this case, this is a process known as thermally activated delayed fluorescence, which I'm not really going to be talking too much about today, but it is an interesting process that's often utilized in devices like organic LEDs, etc. So that's the basics of photoinduced excitation, which is going to be an important concept for this technique. So now I'm just going to jump into an overview of transient absorption spectroscopy. So it's a probe method which is used to study molecular events that happen on the ultra-fast timescale. So this would be from nanoseconds to femtoseconds. And essentially, we're utilizing ultra-fast shutter speeds to allow observation of ultra-fast molecular events. So some examples of those would be energy transfer, electron transfer, which would occur on the nanosecond timescale, photoluminescence, which would occur on the microsecond timescale, intersystem crossing, which would occur on the picosecond timescale, and then other things like bond vibrations that occur all the way down on the femtosecond timescale. So on this slide, I've included two images. So the image on the right here is an image that I acquired from the Nikon website, where they're talking about exposure. And as you can see here, there's two pictures of the same scene. It's like some water crashing down on some rocks. And as you can see here, you know, on the image on the left, we have a shutter speed of 1/250th of a second, versus on the right, we have an image where we have a shutter speed of 1/4 of a second. So you know, as you can see, when we have a much faster shutter speed, the camera is able to capture a lot more of the nuances, you know, of like, you know, the water kind of like splashing in all these different directions. And you get a lot more of a clear image. Whereas here, you know, when you have a slower shutter speed, all of those dynamical nuances end up kind of become blurred together. And so that's kind of the same sort of idea here, is that we need we need an ultra fast shutter speed to capture you know, a lot of the information that you know, occurs at, you know, at these ultra fast timescales. And so here on the image on the left here is it's a compilation of an action sequence where, you know, a bunch of images that were taken at different times of, you know, an action. In this case, it's you know, this kid is doing a kickflip off of a ramp on a skateboard. And I included this image because it kind of represents, you know, a bit how the data is collected in this sort of experiment, where, you know, we're taking snapshots at different times of an event and compiling them together such that we can see, you know, a lot of, you know, how the scene is changing over time. Right. And then, you know, so it's kind of what happens in transient absorption spectroscopy is, you know, we end up taking, you know, a bunch of different snapshots of, you know, of an excited state of your sample, and then we're seeing how it changes in time, and, you know, how, you know, it becomes excited, then it kind of returns back to the ground state, and then, you know, we can kind of gather quite a bit of information about the excited state from that, you know, compiled data set. So now I'm going to go in a little bit into the instrumental theory, and, you know, how we're able to access ultra fast time resolution. So with transient absorption spectroscopy, the instrument requires a component that can change faster than the process that's being investigated. Kind of similar to the, you know, to that picture, to the picture of the water crashing on those rocks. And so in this case, you know, we're going to need a strong continuous wave laser, and you know, we're going to produce that via variable losses. So, you know, in terms of creating such a laser pulse, there's two available engineered solutions that can be applied. And the first is a Q switch, which is a variable attenuator within the laser cavity. And this can produce laser pulses that are several nanoseconds long. And there's three different main types of Q switches. So there's the saturable absorber, which absorbs the laser. So that's shown here in A, where you have this material. It's a light absorbent material that will absorb the laser. And then, you know, once it becomes saturated, then you know, your laser pulse will end up passing through this material and then going into the rest of your experiment. And then you can also have an electro-optic modulator, which uses a polarization controlled material. And so you can control the polarization using voltage. And so what happens is you end up once you build up a strong enough light source or laser, you can switch the polarity on this polarizable material such that you let your laser shine through, and then it can move on to the rest of the experiment, which I'll go into a little bit in more detail in the next slide. And then the third type of key switch is an acousto-optic modulator, which is a piezoelectric transducer, which modulates the refractive index of this material shown here in section C of this image. And so this is controlled by radio frequency. And so when you have the radio frequency on, you end up scattering the light, and then when you have the RF off, you're able to once you've built up a strong enough laser, you're able to pass the light through this material to move on to the rest of your experiment. So there's a second available solution, which is called mode locking of the light modes within the laser cavity. And so this is how we're able to access picosecond and femtosecond pulses. And so I'm going to talk a little bit more about that in this slide here. So mode locking provides a fixed phase relationship between the longitudinal modes of the laser's resonant cavity, right? So typically, with a laser, you're going to have, and I guess the most basic form of laser, you're going to have at least two mirrors, where the light can bounce around, it can constructively interfere, and eventually, once you've built up a strong enough pulse, then you have this continuous wave of photons being emitted from this laser cavity, and so when you mode lock, it acts as a frequency filter where only the wavelengths that satisfy this equation here, so n times the wavelength divided by 2 would be equal to the path length between the resonant cavity. And so only the wavelengths that satisfy this equation will constructively interfere and survive in the cavity. And so an integer number of wavelengths has to fit within the length of the cavity. And so shown here in panel A, we have an example of just some randomly phased modes of light. And so here in panel C, we have shows the field intensity at different distances. And so since we're reflecting back and forth, ideally what we want is for constructive interference to happen at 2 times the length of the resonant cavity, because we're going to have to reflect in order to create the interference. And if you have a bunch of random phases, you're going to end up having field intensities that end up being random. And so for a laser, you want one wavelength, you want one specific wavelength to be compounded on top of each other, on top of itself, to create this laser pulse. But when you have identically phased modes, so you end up generating a pulse that's periodic, and it'll end up building upon itself until it becomes very strong, and then your photons can be emitted from there. And so when you lock in the phases, this ends up creating a lot shorter of a bandwidth. And so here in panel D, you can see that as you add more and more modes that are locked, you end up creating a tighter bandwidth. So that's going to end up creating a stronger laser, and then you can end up getting better resolution in terms of creating these really short laser pulses. So a little bit more in depth into the theory behind the instrument. So like I said before, it utilizes a pump probe method. So you have two different pulses of light, one that's a pump and then the other that is a probe. So the pump serves to excite your sample, and then the probe serves as a constant that where you can observe changes in absorption due to excitation. And so you start with your laser here, and then your light beam ends up going through a beam splitter. So one pathway is going to end up going to your pump pulse, and then the other is going to end up going to your probe pulse. And so there's a chopper here that chops the beam periodically, so that you can measure both the ground state absorption as well as the excited state absorption. And so another thing is that you're going to need to modulate the delay between the pump and the probe pulse. And so as a part of the experiment, as I was kind of alluding to earlier, we need to take measurements at different pulse or at different delay intervals, so that we can get a more complete picture of how the excited state absorption is changing in time. And so here I've shown some equations that explain the intensity of the beam that's detected by the detector. And so you're going to have two different measurements here, right? So like I was saying, you have a chopper so that you can get your excited state intensity as well as your ground state intensity, and that's related to the absorption of your sample. And I just realized that there's a typo here, so this should be the absorption of the ground state sample, because the beam would be blocked here. So what we're measuring is actually the difference between these two, right? So to measure the absorption difference, which is termed as delta A, we're going to need to subtract the ground state absorption from the excited state absorption. And to do this, you can take the log of each of these equations, right? So then you can end up getting your absorption values, and then you're left with this equation here. And so now I'm going to talk a little bit about the spectral features of transient absorption spectra. And so the spectra contain three main spectral contributions of ground state bleaching, which occurs from the ground state absorption signal being bleached by excitation. And you have stimulated emission, which is caused by your excited sample emitting photons. So basically this would imply that your sample in its excited state is photoluminescent. And then there's induced absorption, which is produced through further excitation of excited states. So this is also called excited state absorption. So I'm going to talk a little bit about these three in more detail in these coming slides. So ground state bleaching is going to end up contributing negatively to the signal, to your ground state absorption signal, because now the concentration of your ground state species is going to be decreasing as you begin populating the excited state. So that's shown here in this in this green area. Right, so we have a negative delta A for ground state bleaching. And then, so for stimulated emission, like I said, if your sample is photoluminescent, then it's going to emit photons. And so in this case, it's also stimulated emission is also going to be a negative contribution to your absorption signal, because since we're measuring absorption, if your sample is emitting photons, then you're sending more photons to the detector, and so that's gonna appear in your data as as a negative contribution to the signal. And then also this signal is going to be redshifted because of some of the non-radiative decay that occurs due to some of your excited state going back to the ground state non-radiatively. And so here, this is going to be a negative delta A contribution, and this is just because at this point the excitation intensity is going to be higher than the ground state intensity, right? And so if you look here, if this number is higher, then we're going to end up having we're going to end up having a negative number come out of this equation. So that's going to be another negative delta A contribution. And then finally, we're going to have induced absorption, which correlates to further excitation of excited states. So this is where additional absorption of excited states occurs, where you're forming even higher excited states. And so this is also assuming that these excited states are non-emitting, right? Because if it emitted photons, then you might end up actually seeing a negative contribution here. But so for these non-emissive or these non-emitting excited states, this could be due to a structural change of the ground state. So say like isomerization of say like an alkene or something like that, or access of new electronic excited states. And so being able to observe these types of excited states is one advantage over time-resolved fluorescence, which is another type of time-resolved spectroscopy. But your sample doesn't necessarily need to be photoluminescent in this case, or these excited states don't necessarily have to be photoluminescent to be able to observe these changes in the absorption. So for data processing and analysis, so this is a spectroscopic method. So we're going to have you can represent this data either in the frequency domain, through a Fourier transform, or in the time domain using an inverse Fourier transform. And depending on what you're trying to get out of your data, that's you can see the data represented in either of these domains. Another important thing for the transient absorption spectral data is if you want to get kinetic information if you want to get accurate kinetic information out of it, you're going to need to fit this data to a kinetic model. So this kinetic model is going to have to take into account the instrument response factor. So this is going to be the convolution of the pump pulse and the detector response, or just the pump plus the probe signal. And then so that's going to be instrument specific. So that information is going to need to be taken into account. And then you're also going to need to utilize these decay associated spectra, so these are models of exponential decays and amplitudes that can be convoluted with your incident response factor. And so there are specific models that are used specifically for difference absorption spectroscopy, which transient absorption is one of those methods. And so compiling all of that, you're able to construct what's known as a species associated spectra. By comparing several models, several different models to your experimental decay data. And so, you're going to need some amount of intuition to kind of figure out the best way to optimize, fitting this data to to a model. But here in this figure, so I have shown. So this is going to be, this is the transient data taken at different pulse lengths, and so we're basically measuring the decay process, right? So we need to go. So it's like we need to go from from our ground state to the excited state, and then we're going to measure the decay. And so this is going to be the time domain at different different pulse lengths, and then basically you're able to you're going to be able to fit your data to some sort of model that looks something like this. So then you can generate your species associated spectra, and then from there you're able to account for the instrument response, as well as fit a model that represents your system. So you're going to have some sort of idea as to like what types of processes that you're going to be investigating to be able to find the correct model. So now I want to move into talking about the utility of this method in photocatalytic organic synthesis. So here I've repasted the Jablonski diagram just for reference, but basically for photoredox chemistry specifically, your photocatalyst is going to be excited to an excited state, and so in the case, so photocatalyst can act, or photoredox catalyst can act as either an excited state reductant or an excited state oxidant, right? So in this case, if your photocatalyst is acting as a donor, an electron donor, then it's going to be acting as a reductant in its excited state. And so at this point, we've created a cation or a radical cation of our photocatalysts, and a radical, like an anion or radical anion of whatever reaction component that the photocatalyst reacted with. And then correspondingly, if your photocatalyst is acting as the acceptor in its excited state, then it's acting as an excited state reductant, where again you end up forming either like a radical cation radical anion pair, or a cation anion pair, etc. And so to kind of put this more into context, so one of the most commonly known photocatalysts in organic photocatalysis is rubipi. So this is it's a transition metal complex. It absorbs in the visible light range at 452 nanometers. It has a stable and long-lived excited state, which is favorable for catalysis, because you want that excited state to exist long enough to be able to participate in the reaction catalytically. And so rubipi has an excited state lifetime of 1100 nanoseconds, and it acts as a single electron transfer catalyst. And in its excited state, it is an effective oxidant and reductant. So here I've kind of have that same sort of scheme that I had in the previous slide, but kind of put in more into context of RBIPy. And so upon absorption of a photon, and after intersystem crossing to access a triplet excited state, you end up with these spin decoupled electrons. And in this state, the RBIPy can act as an oxidant with a redox potential of positive 0.77 volts, and also as a reductant with a redox potential of negative 0.81 volts. And so you can kind of see that here. So it can oxidize some sort of reaction component to generate RBIPy plus, or it can reduce reaction component and generate RBIPy 3 plus. And so that's kind of shown here in this scheme here. So you have ground state RBIPy, which is in a +2 oxidation state, and then upon excitation with visible light, it can act as either an oxidant or reductant. So it can be quenched, as they say. Excited state can be quenched either oxidatively or reductively. And so if it's oxidatively quenched, then that means that it's being oxidized by some reaction component, to form RBIPy 3, and then to close the catalytic cycle, it's going to have to be reduced by some other reaction component to get back to its ground state, and then correspondingly to go through the reductive quenching cycle, the excited state RBIPy would have to be reduced by some reaction component to form a RBIPy plus intermediate, which can then be reoxidized by some other reaction component to complete the catalytic cycle. So that's the basics of how photoredox catalysis works. And I just wanted to show this table as well that shows a variety of different transition metal catalysts that are quite popular right now. And the main thing I wanted to focus on for this figure is just this column here, where they show the excited state lifetime of these different photocatalysts. Where some of them are have quite long-lived excited states. So we've even gone past RBIPy, with some of these iridium catalysts, and so these excited state lifetimes were measured using transient absorption spectroscopy. So that's where that fits in. And of course, all these redox potentials were generated using cyclic voltammetry. So now I just wanted to talk about just a literature example. It's a JAX paper that came out in 2018 from Abigail Doyle's group from Princeton. And it's titled "Long-Lived Charge Transfer States of Nickel-2 Aryl Halide Complexes Facilitate Bimolecular Photo-Induced Electron Transfer." So this is kind of a cool paper because this is kind of like a mechanistic study on this reaction that they had. It's a reaction methodology that they published previously, and they use transient absorption spectroscopy to probe the mechanism and kind of like learn some pretty interesting features about how this reaction is proceeding. So basically they're coupling an aryl halide with an alcohol to form an aryl ether through nickel redox catalysis and light under basic conditions. And so here, I just want to start off with this figure that they showed here, where they kind of draw some similarities between D8 nickel complexes and like iridium, like the precious metal electronic structure. And so it can undergo a metal to ligand charge transfer event. And so the similarity occurs because because you have this pi star orbital of the diterbial Y purity ligand lies below the metal d orbitals, and so this kind of gives way for a visible light photocatalysis. It generates a relatively long-lived triplet excited state of 10 nanoseconds. So it's not quite as long-lived as the iridium catalyst, but it is sufficiently long-lived enough to do photocatalytic chemistry. And in this case, it's doing photo-induced electron transfer. So here they have some absorption spectra of just the ligand, and they have the dichloro version of the nickel complex, and they have the oxidative addition complex here. And so one thing to note with the ligand is that you have this this transition here would correspond to the pi star transition of just the ligand, and so I'll come back to that a little later. And then here they just showed that there is a relative difference between when you substitute the halide. But I'll move my face over here. Over here they've done some DFT calculations on the absorption spectra, and so they've calculated all of these different computational transitions. They've also calculated the charge density. So this delta nickel is just talking about the difference the difference between nickel 2 and nickel 3 in these excited state transitions. They've also generated a nice molecular orbital picture here with these calculations, and also important to note that this calculated spectrum agrees quite well with the experimental spectrum. So here, so now we're actually getting into the transient absorption data. So here in panel A, we're looking at basically like a heat map that it corresponds to the different time intervals that this experiment was run at. So this was at this was at a pump pulse of around 295, I believe, which would correspond to the pi star transition of the ligand, Dr. butyrylpyridine. And so then here they actually have some transient absorption spectra where they've done just the ligand, and then they have the dichloro complex, and then they have the oxidative addition complex here with the aryl group. Yeah, so they're all different. And in panel C here, they have the single wavelength kinetics for both the dichloro complex as well as the oxidative addition complex. And so this was done also at a pump pulse at 295 nanometers. And what they've also shown here is that they have the experimental they have the experimental transient absorption spectra shown in purple here, and then they have a calculated version of this shown in the dotted blue line. And so basically all they were trying to show here was that these agree, so that their computational model is in agreement with experiment. And so here now we get to start. Now we get to see some of the time slices of the excited state. And so here, they have, so this is just initial cooling. So this is this is in fractions of a picosecond. We're just seeing some, we're just seeing, some thermal relaxation occurring here. But so these were done with a pump pulse wavelength of 400 nanometers, which corresponds which corresponds to the excitation to the singlet excited state. And so, upon relaxation, or upon cooling, you end up getting to, this cooled singlet excited state. And then from here, it's going to undergo intersystem crossing. Right, so in this 0.8 to 1.8 picosecond range, they do start to see the relaxation, some relaxation occur. And so this corresponds to intersystem crossing. So this would be the spin flip from the singlet excited state to the triplet excited state. And so they also noted that between 2.5 and 16.5 picoseconds, that they saw some bleach broadening, right? So it's kind of that ground state bleaching signal contribution that I was speaking about earlier. They've noticed that it's starting to broaden, and they noted that this is indicative of the formation of an excimer, which I'll get to in the next couple of slides here. I'll explain that in a little bit more detail. But then finally, you have your decay, which happens in the the 0.1 to 6 nanosecond range. And so that would correspond with this transition here. So you're decaying from the triplet excited state back down to the singlet ground state. So next, so they wanted to account for some decomposition products that they saw upon irradiation at wavelengths that correspond to the reaction that they're running, and also thermal decomposition. So they did this in deuterated THF because they measured the they measured the concentrations of these products using proton NMR. And here in this column, they have the percent conversion of 1Cl. And so you can see here that there's not really too much turnover here with just thermal activation, but there is some. But you don't really see any of these decomposition products. And then, under the irradiation conditions, you see a much higher percent conversion of this complex to these conversion products. And so all of these conversion products are mostly a result of reductive elimination, right? So you can either have I guess aryl coupling to form these biaryl compounds, and you can have coupling between the aryl substituent here and THF. And so so in a previous I guess somewhat unrelated paper, they showed that this complex can also undergo photoelimination of a chlorine radical. So that's effectively how this THF radical can be formed. And then that THF radical can add in to the nickel complex, and then you can reductively eliminate to form this aryl THF bond. And they also showed that there is a radical cage pathway where you can eject an aryl radical. So I suppose that could also generate this THF radical while also forming a deuterated aryl compound. And so in panel B here, they showed that there is a pretty strong correlation between the rate of the decay of the excited state and the concentration of the nickel. And so there should be no nickel concentration dependence expected if this was a unimolecular decomposition event. or if it was with just direct reaction with solvent. And so this indicates, that there's some sort of this should be bimolecular, sorry, it's a typo, indicates bimolecular photoinduced electron transfer, where the excited state is directly quenched by the ground state version of this this nickel complex. And as you can see here, there's it's not a linear correlation, but rather there's kind of like a saturation curve that indicates some sort of like Michaelis-Menten like kinetics, and so that kind of goes along with the formation of this excimer, which is shown here, and which they indicated with the bleach broadening, in a couple of slides ago. And so here, in panel C, you start with your triplet excited state of this nickel aryl halide complex. So there's a couple of different pathways. You can relax all the way back down to the ground state, or you can form this excimer with another ground state complex to form this excimer, which can decay back down to two ground state complexes, or it can, an electron transfer event can happen between these two complexes to form, a nickel 3, and a nickel 3 version of this ground state complex, and then a nickel 2 version of your excited state complex, where the ligand is still reduced, right? So this is a metal to ligand charge transfer event. So in the excited state, there's electron densities being pushed from nickel to the ligand, and so that's where this is coming from. And so from here, now we have nickel in a sufficiently high oxidation state to where it can undergo reductive elimination to form these decomposition products. And so to put that all together, they kind of wanted to reiterate that reductive elimination from a nickel 2 complex is not very thermodynamically favorable, because as you can see here, there's a delta G for this process is going to be positive 45 kcals per mole, which is pretty unfavorable as compared to if you have a nickel 3 complex. Now this reductive elimination step, to form your coupled product, and then to form nickel 1 through the reductive elimination is a lot more thermodynamically favorable, and even it's spontaneous, right? So you have a negative delta G here, and so here they've shown the reaction scheme again, and they noted that this reaction still produces yield in the dark, albeit substantially less yield than in the under the irradiation conditions. But to tie all this information together, they have this proposed mechanism where you have your you start with nickel 0, so they have their nickel cod 2 ditert-butylbipyridine, or the nickel cod ditert-butylbipyridine, where the aryl halide can oxidatively add into the complex, forming nickel 2 intermediate. And then this nickel 2 intermediate can be excited, and it can form the excimer that I was talking about before, with a ground state version of this complex, where electron transfer can happen. And then they propose this radical cage pathway, where an aryl radical can be ejected from this oxidative addition complex to form a nickel 1 species. And this nickel 1 species can undergo ligand exchange with the alkoxide that's formed, with the alcohol under basic conditions, to form this nickel 1 alkoxide intermediate, which can undergo oxidative addition with another aryl halide to form this nickel 3 intermediate, which can then undergo reductive elimination form your aryl ether, the coupled product, and then you can basically, now you're on cycle, for this to continue happening. And so the radical cage pathway can operate alone without light, albeit a lot slower. And so that was their justification for seeing some of this in the dark. It's kind of interesting how they were able to utilize transient absorption spectroscopy to to kind of dig a lot deeper into the mechanism of this reaction, because it's kind of a unique mechanism. And it also showcases that you can use nickel as a photocatalyst, which is useful because instead of using ruthenium or iridium, it's a lot cheaper to use a base metal like nickel to do this sort of chemistry. So to summarize and conclude, transient absorption spectroscopy is a useful tool to analyze dynamics of ultrafast molecular processes. It uses a pump probe setup to elucidate changes in absorption due to photoexcitation. Data fitting is required to extract kinetic data for excited state decay. And this method can be applied to photocatalytic reaction methodology development, as well as catalyst design and organic synthesis and organic photocatalysis by measuring the excited state lifetimes of photocatalysts, by also distinguishing key mechanistic steps by considering the established timescales of various molecular processes, and lastly, by providing insightful information about how excited state electronic structures and quenching behaviors without necessarily measuring the emission spectra. And so that concludes my presentation. So I'd be happy to take any questions. So if you guys have any questions, or you can either find me in Biodesign C, or you can feel free to shoot me an email here at narmada@asu.edu, and I'd be happy to take any questions about this, because I think this is a really interesting topic. So thank you.